Hi my dear students, welcome back to the class. So far we were discussing about three-dimensional geometry, isn't it? We derived various formulas to find the shortest distance between two parallel lines, two skew lines and two intersecting lines. Also we derived certain conditions for find the angle between two lines, and we solved exercise 11.2 in the previous class. In this class, we are going to derive, or we are going to find the conditions to derive the equations of a plane. See, in the last class we derived the equation of a line, whereas in this class we are going to derive the equation of a plane. You know various kinds of planes, xy plane, xz plane, yz plane, so just like this. So now you know how many planes, a variety of planes, and you know to give the examples of planes like xy plane, etc. In this class we are going to derive the equation of any plane, that not necessarily xy or yz plane, any plane can be, the equation of any plane can be derived after attending this class. So without any further intro, let us move on to the class. So now we are going to derive the equation of a plane. Equation of a plane in normal form. Equation of a plane in normal form. Of course, you can see the name is something particular. Equation of a plane in normal form. See, in normal form. Here we are. In normal form, we are provided with a plane with perpendicular distance from the origin. That is, if we are given with a plane and also we are given with what is the perpendicular distance from the origin, then we can easily derive the equation of the plane using the steps now we are going to do. Suppose that this is the plane we are provided with. You can see a bigger plane here, not a triangle. This is a two-dimensional plane, and this is the plane we are provided with. And suppose that ON is the perpendicular distance from the origin to the plane. These are the only given condition. See, we are given with a plane and only perpendicular distance from the origin. Now we are going to find the vector as well as the Cartesian equation of the plane. Suppose that we are given with a plane and the perpendicular distance from the origin to the plane is nothing but d. Okay. Now let P of x, y, z be any arbitrary point in the entire plane. See, P be an arbitrary. I told you that in order to derive an equation, we always choose some arbitrary points. Here the arbitrary point in the plane is nothing but P of x, y, z. Okay. Now let the position vector of P be vector r. So the position vector of P is given by the vector r, and these conditions have been derived by us. What all things are provided? A plane and a perpendicular distance only. Nothing else is given. So the other things are derived by us. So the position vector of P is given by r. Then by triangular law of vector addition, we know that, see, this is a vector and NP is a vector. See, P is an arbitrary point, N is a point on the plane which gives perpendicular distance. So NP is a vector in the plane, ON is a perpendicular vector. So by triangular law of vector addition, we have ON, vector ON plus vector NP is equal to the vector R. Okay, now let it be there. Now see, distance of ON is d. Let n cap be the unit vector in the direction of ON. That is, n cap is the unit vector in the direction of ON, and the distance of ON is d. Therefore, the vector ON is nothing but d into n cap, isn't it? See, n cap, what is n cap? N cap is the unit vector which is in the direction of this, and d is the distance of the vector ON. So ON is nothing but d into n cap, isn't it? Now we shall just substitute that value here, d into n cap plus vector NP is equal to r, right? Therefore NP, vector NP is nothing but r minus dn cap, right? Now see, ON and NP are perpendicular vectors, isn't it? See, ON is the perpendicular distance and NP is a line in the plane. So ON is perpendicular to, we know that ON is perpendicular to NP, isn't it? Therefore, ON dot NP is equal to 0. Right, since two vectors are perpendicular, then their dot product must be equal to 0. We know that result. Therefore, ON is perpendicular to NP. Therefore, ON dot NP is equal to 0. Now, what is ON? ON is equal to DN cap. DN cap dot NP. What is NP? R minus DN cap. R minus DN cap is equal to 0. Since D is a scalar, D is a number, D cannot be equal to 0 since D is the perpendicular distance. So D cannot be equal to 0. Therefore, it will result in N cap dot R minus DN cap is equal to 0. Right. See, since D not equal to 0, we can conclude that D cannot be equal to 0. So the rest quantity will be equal to 0. Now we can open the bracket. It will become R dot N cap minus D into N cap dot N cap is equal to 0. Now we know that N cap dot N cap, it is nothing but 1. Since angle between them is 0, cos 0 is 1, mod N cap is 1, mod N cap is 1. See, N cap is a unit vector. Therefore, this will become R bar dot N cap minus D is equal to 0. Therefore, we get R bar dot N cap is equal to D, or D is equal to R dot N cap will be the vector equation of the plane whose perpendicular distance is given by D, and N cap is the unit vector in the direction of ON. R bar is the position vector of the arbitrary point. Now we shall derive the Cartesian equation. The vector equation is given by R bar dot N cap is equal to D, isn't it? Where R bar is the direction, position vector of the arbitrary point x, y, z. Therefore, we shall name R bar is equal to xi cap plus yj cap plus zk cap, isn't it? See, x, y, z, xi cap plus yj cap plus zk cap. And let L, M, N be the direction cosines of N cap. Therefore, N cap is nothing but Li cap plus Mj cap plus Nk cap. See, this is not given. We are just putting this into the derivation process. So, we get N cap. Now, we shall find what is R bar dot N cap is equal to D. Therefore, on substituting all these quantities together here see R dot N. See, in order to find the dot product of two vectors, it is enough to multiply the respective components and add them together. So, Lx plus My plus Nz is equal to what? D. So, this is the Cartesian equation of the line, equation of the plane whose direction cosines, direction cosines of the perpendicular distance is L, M and N, and the arbitrary point is X, Y and Z, and D is the perpendicular distance from the origin to the point. So to the plane. So this is the Cartesian equation of the plane whenever we are given with the perpendicular distance and the unit vector. See, if we are given with the unit vector in the direction of the perpendicular distance, easily we can obtain the direction cosines, and hence we can form this equation. So here we have vector equation as well as Cartesian equation. Now we shall do some problems using these two. Now we shall move to the example number 13, and the question is find the vector equation of the plane which is at a distance 6 by root 29. So the distance D is equal to 6 by root 29 from the origin, and its normal vector from the origin is, so normal vector from the origin is given by, from the origin is equal to 2i cap minus 3j cap plus 4k cap. So we are given with the perpendicular distance from the origin, and the normal vector from the origin is that. Okay, see, we know that the vector equation of the plane is given by R bar dot n cap is equal to D. Here D is already given. Now we want to find n cap. See, we are given with normal vector. We know that n cap is the unit vector in the direction of the normal vector. So we can easily find n cap is equal to the normal vector by its magnitude. That is 2i cap minus 3j cap plus 4k cap whole divided by square root of 2 square plus 3 square plus 4 square, because n cap is nothing but the unit vector in the direction of the normal vector, and normal vector is given. So in order to find the unit vector, just divide that unit vector, divide that vector by its magnitude. It is equal to 2i cap minus 3j cap plus 4k cap whole divided by, what is this, 16 plus 9, 25 plus 4, 29. So 20 root 29. Therefore, the vector equation is given by r bar dot, what is n cap this is. So 2i cap minus 3j cap plus 4k cap whole divided by root 29 is equal to, what is the 6 by root 29. So this is the vector equation of the plane whose perpendicular distance from the origin is 6 by root 29. Now coming on to the example number 14. Find the direction cosines of the unit vector perpendicular to the plane whose equation are. See, we have to find the direction cosines of the unit vector, and the equation of the plane is given by r dot 6i cap minus 3j cap minus 2k cap plus 1 is equal to 0, passing through the origin. So this is the equation of the plane. First of all, in order to deal with such problems, we have to transform the equation into the standard form. So we know that this is the standard form of the equation of a plane, right? So we are going to transform this. This is equal to r bar dot 6i cap minus 3j cap minus 2k cap is equal to minus 1. See, this is of the form this, but here we have n cap, but here it not necessarily n cap. So this is the required vector. Let it be m. So vector m is equal to 6i cap minus 3j cap minus 2k cap. It is not a unit vector. It is clear that we can find the magnitude of this. It is 36 plus 9 equal to 45 plus 4 is equal to root 49 is the magnitude of this vector. So this is not a unit vector. So in order to make it into a standard form, we have to make this vector into unit vector, right? So n cap is equal to 6i cap minus 3j cap minus 2k cap divided by its magnitude. What is its magnitude? 6 square 36, 3 square 9 plus 4. It is equal to 6i cap minus 3j cap minus 2k cap whole divided by root 49, isn't it? See, now it becomes r bar dot n cap, where n cap is this equal to d in the formula. Therefore, the direction cosines of n cap is equal to, what are the direction cosines? 6 by root 49, this is L, m is equal to minus 3 by root 49, and finally n is equal to minus 2 by root 49, which are the direction cosines of the unit vector perpendicular to this plane. So such problems, if this is a unit vector, then nothing to fear, just write the direction cosines of this unit vector directly. But here we can easily observe that this is not a unit vector. That's why we divided the vector by its magnitude in order to get the unit vector. Now we shall move on to the next example. Coming on to the example number 15, the question is that find the distance of the plane 2x. See, find the distance of the plane 2x minus 3y plus 4z minus 6 is equal to 0. Note that this equation is in the Cartesian form. We know that the equation in the Cartesian form for a plane is Lx plus my plus nz is equal to d, whereas L, m, en are the direction cosines of the unit vector, isn't it? Of the unit vector in the direction of the perpendicular. In the direction of the perpendicular distance. But see, this is not a unit vector. So in order to find the unit direction cosines of the unit vector in the direction of the perpendicular distance, we have to divide this entire distance. See, we can modify this equation as 2x plus 3y plus 4z equal to 6. But since these coefficients, this is not L, this is not M, this is not N, but actually L, M, N are the direction cosines of the unit vector n cap. So in order to make the direction cosines of the unit vector, we have to divide each of the term by the entire magnitude, that is root of 2 square plus 3 square plus 4 square equal to root of 4 plus 9 plus 16 equal to root 29. So the equation should be changed in the standard form as 2 by root 29x plus 3 by root 29y plus 4 by root 29z equal to 6 by root 29. See, we have divided the both sides of the equation with the root 29. So this equation and this equation are exactly the same. But here we have the coefficient are nothing but the direction cosines of the unit vector, because the magnitude L square plus M square plus N square equal to 1, as well as the magnitude of the corresponding vector is 1. Here it is not equal to 1. Therefore, we can say that the direction cosines L is equal to 2 by root 29, M is equal to 3 by root 29 and N is equal to 4 by root 29. And in that case, we have the distance is nothing but 6 by root 29. So that's the example number 15. Very simple. Always remember this. Whenever we are given an equation of the plane, try to make it into the standard form. Then whatever be in the standard, what all things we have obtained in the standard form will be the answer. Now coming on to example number 16. Find the coordinates of the foot of the perpendicular drawn from the origin to the plane. We are given with a plane 2x minus 3y plus 4z minus x equal to 0. So consider this is our required plane. We have to find the foot of the coordinates of the foot of the perpendicular. See, this is the origin and suppose that this is the perpendicular to the plane. Then we have to find the coordinates of this point. Let us name this point as P of x1, y1, z1. So we have to find x1, y1 and z1. Whereas the plane, equation of the plane is nothing but this. First of all, we are marked the point here as x1, y1 and z1. Therefore, direction ratios of the point P is nothing but what? x1, y1 and z1, right? So the direction ratios of the point P is nothing but x1, y1, z1, because the position vector of the point P is nothing but x1 I cap plus y1 j cap plus z1 k cap. Now we are given with the equation of the plane as this. We can make this into a standard form, that is 2x minus 3y plus 4z equal to 6. Now we can make it into a unit vector form. So in order to make, so we have to divide this left hand side and right hand side with the magnitude of this vector. So it will become square root of 2 square plus 3 square plus 4 square. It is equal to square root of 29, isn't it? So we can divide the left side as well as right side of this equation with square root of 29. So it will become 2x minus 3y plus 4z whole divided by root 29 is equal to 6 by root 29. See, now this is in the standard form of the equation of the plane. Now from it we can have the direction cosines of this line OP as direction ratios of OP as OP vector OP is nothing but 2 by root 29 comma minus 3 by root 29 comma 4 by root 29. Now since this is the direction ratios of the line OP and also we have the direction ratios of P as x1, y1 and z1, which means that we are given with two direction ratios of the same line OP, right? Therefore, the direction ratios must be proportional to each other. We know that the direction ratios, a line can have infinitely many direction ratios, but the only condition is the respective direction ratios must be proportional. We learned it, right? So we have x1 divided by 2 by root 29 is equal to y1 divided by minus 3 by root 29 is equal to z1 divided by 4 by root 29 is equal to a real constant, say k. Now therefore we can have x1 is equal to 2k divided by root 29. See, x1 by 2 by root 29 is equal to k. Therefore we have x1 is equal to this, y1 is equal to minus 3k divided by root 29 and z1 is equal to 4k divided by root 29. Now we can substitute x1, y1 and z1 in the given equation. See, this equation is nothing but the equation of the plane. So it must satisfy every point. Now x1, y1, z1 is a foot of the perpendicular as well as it is a point on the plane. So we found out x1, y1, z1. So when we substitute that values here, then this equation must satisfy it, right? After substituting and solving for k, we will get k is equal to 6 by root 29. What we have to do in order to find k? Just pick all the values x1, y1 and z1 and substitute here. You can solve it here and you can easily find the value of k. Then therefore we have x1 is equal to 2k. We are going to substitute the value of k here. So 2k by root 29. 2 into 6. 2 by root 29 into what is k? It is 6 by root 29. It is equal to 12 by 29. Similarly, y1 is equal to minus 3 into, y1 is equal to minus 3 into 6, minus 18 by 29. Similarly, z1 is equal to 4 into 6 equal to 24 by 29. That's it. x1, y1 and z1. x1 is equal to 12 by root 29. y1 is equal to minus 18 by root 20, not root. x1 is equal to 12 by 29, y1 is equal to minus 18 by 29 and z1 is equal to 24 by 21 are the coordinates of the foot of the perpendicular to the plane thus. So, നിങ്ങൾ ഓർക്കേണ്ട ഒരേ ഒരു കാര്യം ഇത്രേ ഉള്ളൂ. ഇവിടെ നിന്ന് നമ്മൾ എന്താ ചെയ്തത് x1, y1, z1 are being substituted here in order to find the value of k. Since x1, y1, z1 is a point in the plane and this is nothing but the equation of the plane, it must satisfy x1, y1, z1. So that's it. We have solved, found out equation of various planes in vector as well as in Cartesian form. So I am winding up by this. We shall learn further about planes and equations of plane angle between planes in the further classes. So until then, watch these lectures very well and study hard. So till then, bye bye.